So students, so today we are going to start this CHM 321 lecture 1. The first discussion which we are going to begin with is the very simple thing, that is Arrhenius equation. And most of you know this simple Arrhenius equation, that is, I can write it this equation as like K A e to the power minus E A by RT. In this equation, all of you know most probably that K is the rate constant, A is the pre-exponential factor, EA is the activation energy, R is the gas constant, and T is the temperature, and I can write it like absolute temperature, right? So what this equation is telling us, this equation is basically is required for us to understand the temperature dependence in kinetics. So roughly looking at this equation, one can say that the rate constant is strongly dependent on the temperature, right? So as we increase the temperature, the rate constant, the rate of the reaction is going to be faster. Okay? And specifically, if we look at the exponential part, which is this part, so this part is basically suggesting there is an activation energy is required to overcome for a reaction to happen. Okay? And I will leave it up to you guys to determine the unit of this exponential term, and you guys hopefully know that this exponential term doesn't have any unit, and there is a pre-exponential factor is present which represents the maximum rate constant possible. So the unit for K and A will be same. So for a first order rate constant, K and A will be second inverse. Okay. And if we go to like second order reaction, it will be mole inverse, second inverse. So second order, it will be mole inverse, second inverse. Then for third order, it will be mole inverse to the power minus 2, second inverse. So this is the way it will continue. So if we try to understand what is going on here, what is activation energy in a simple graph, we usually plot like potential energy on the y-axis, and on the x-axis is the reaction coordinate. And all of you know, so say for example, this is how the reaction profile looks like. So this is the energy level for the reactant, this is the product, and this energy difference is basically known as EA. Okay, so R is for reactant and P is for product. Okay, so basically this graph shows that in order to convert the reactant to the product, we need to overcome our energy barrier. And this energy barrier, we know it as EA, or the activation barrier. Now the top of the hill, I can write it as like this way, which suggests this one is basically usually is called activation state. Okay, so I hope all of you already know these basic things from your school level understanding, that whenever in kinetics, basically the reactant wants to convert it to the product, you need to have a activation, usually have a activation barrier, and that activation barrier has been drawn here. So this is the basic concept behind this Arrhenius equation. So now, now if we move forward and we move forward and try to expand this equation, then what we can do is that what we can write this equation as, like, you know, we have written this equation k a e to the power ea by rt. So we can write this equation as ln k is equal to ln a minus ea by rt. You can further write this equation as like log base 10k is equal to log 10a minus ea divided by 2.303 rt, right? So now according to this equation, if we try to draw a graph, and on the y-axis where we will plot it like log 10k, and on the x-axis we will plot like 1 by t. And so now this is the equation of a linear equation. So we will get this type of a linear graph, and the slope of this graph will be ea by divided by 2.303 r. Okay, so by measuring, I can say by measuring by measuring log K, log 10K versus temperature 1 by T, we can determine EA of the reaction, where EA is the activation energy. So this EA could be in the unit, could be kilojoule per mole or kilocalorie per mole. So more or less we have this understanding that every reaction has some kinetic barrier, and that kinetic barrier is known as activation energy, and that we can determine by through a temperature dependent study, um, and by measuring the rate constant at different temperature, you can determine what will be the activation barrier for this reaction. Okay, so if basically the activation energy is very high, then you know that the reaction will proceed very slowly, and as we increase the temperature, the reaction becomes fast. So this is the basic concept of Arrhenius equation. And now if we go try to understand that about the physical chemistry, that most of this equations, as I have said that in CHM 221 also, that most of the equation, many equation has a pre-exponential factor and then an exponential factor. Exponential factor represents a barrier, a difficulty of doing a job, and the pre-exponential factor represents if we don't have this barrier, then what will be the situation. Okay. It's like our life, that in our life we have certain difficulty, and that difficulty is represented by the exponential term, and if we don't have difficulty, then what is the maximum we could have achieved, that is basically is the pre-exponential factor. So pre-exponential factor A represents what is the maximum possible rate constant. So for example, for a first order reaction, this value of pre-exponential factor is like 10 to the power 13 second inverse. Okay, so this pre-exponential factor represents that if we don't have barrier, then we could have achieved a rate constant of 10 to the power 13 second. Okay, and now obviously the values of the rate constant will be actually much lower than 10 to the power 13 because of this exponential factor. Okay, so as the activation barrier will be higher and higher, the rate constant will be slower and slower. And second thing is that as we increase the temperature, then the rate constant becomes fast. Okay, so this is the basic understanding which is required about the Arrhenius equation, and obviously I hope all of you know the fundamental understanding. Uh, so now, if I ask this question, that why activation energy is required, right? So in order to answer this question, we have to understand that chemistry is mostly, we can say, is about bond breaking or bond making. Okay, So usually the activation energy comes because we need to perform this step, that bond breaking. Okay, so I can say that bond breaking, this phenomena comes because of bond breaking phenomena. Okay, so this activation energy is required because we need to break a bond, right? So for a bimolecular reaction, I can say that these molecules need to collide with each other. Okay, and they need to basically collide with certain kinetic energy, then only the bond breaking can take place, and that is why we need this activation energy, and that is where this states comes. Okay, and if it is for a unimolecular reaction, then uh, then you also need a certain minimum energy required for certain transformation. You need molecules to require certain minimum energy is required for isomerize or decompose. So that is why also you need the you need the activation energy. Okay, so if I have to answer this question, that why activation energy is required, right? So this is our question. So I can say that for a bimolecular reaction to happen, to occur, the molecules must collide with certain kinetic energy so that bond breaking can take place. And hence, an activation energy is required. Okay, so for even for a and for unimolecular reaction, reaction also certain amount of energy is required for isomerization or other transformation to take place. Okay, and so this is the reason that why we need an activation energy for a reaction to take place. Okay, So this is basically today we are covering a very simple topic of Arrhenius equation, which most of you know uh, that about this phenomena, and you also know that this phenomena is very well known phenomena of this Arrhenius equation. So now the next question, so that is what we are covering, and then in the next class we will cover the Riemann hypothesis. So now the next question is that, is it possible for a reaction to not have any activation energy? I think in every class we'll try to learn something new. The answer to this question is that a barrier-less process is okay. Because if we truly understand what I have written here, then you will able to understand that genuinely it is possible that a barrier-less reaction is possible. Okay, why? Reaction or EA is equal to 0 kilojoule per mole is possible. Okay. Many students, whenever we ask this question, they say that this is not possible. Because if we understand what I have written in this page, then we can easily speculate that this is possible. Okay. For example, if I take like I dot plus I dot, and they will form like iodine molecule. Okay. So what is happening is that two radicals are combined, right? So in this process, we are not really doing any bond making or bond breaking, right? No bond breaking required. Is required, and hence this is almost for this reaction almost equal to zero. Okay? Actually, it has actually slightly negative activation energy. Okay, so this is very, very fascinating information, that always we think that we need a positive activation barrier. But here in this case, the thing is uh, that this reaction doesn't require any positive activation barrier, because here in this case what is happening is that two I dot needs to just collide, and you are not really we are not really breaking any bond, and hence in this process we don't have any activation barrier, and so the EA is almost zero. Rather, it has a slightly negative activation energy, because as we increase the temperature, they don't able to collide with the proper orientation. So actually, as we increase the temperature, the randomness increases, and they are not able to collide with each other in a proper orientation, and that leads to less iodine formation. Okay, and that's why it has a slightly rather negative activation energy. Okay, so today this is up to this we want to discuss, and I hope you guys have learned something new. This is the information which is something new. So this is where we will basically stop. So briefly, what we have discussed is that as we increase the temperature, um, if we increase the temperature, then the K increases, right? So this is what the Arrhenius equation tells. And as also we know that as the activation barrier becomes smaller, then the reaction will be faster. Okay? And we also highlighted why activation energy is required, because activation energy is required because we need to overcome a barrier, and this barrier comes because we need to understand, truly understand this one simple comment, which is very very important to understand, is that chemistry is mostly about bond breaking or bond making process. Okay, so for this reason, we require an activation barrier. And if we think about this comment very, very carefully, then we can understand that there are some reaction which in which we don't really require a bond breaking and bond making is required. And in that case, we can have a barrier-less process or a activation-less process also. Okay, so further, in order to understand this kinetics, we need to understand really truly the collision theory and transition state theory, which we will discuss in later classes. So in the next class, which we will discuss about the Lindemann hypothesis, which is about the unimolecular reaction, right? So here we are, what is Lindemann hypothesis is all about, right? That we are saying that, we have, whenever we talk about this kinetics, we understand that the two molecules collide, right? The two molecules collide, so and they can form. We can have transition state theory or collision theory. So then, how the unimolecular reaction takes place, where we don't really have two molecules. Okay, so that is the question has been addressed by Lindemann in his hypothesis about the unimolecular reaction, which we will discuss in the next class. Okay, I hope all of you like this class. So this is where I'll stop today, and tomorrow, if you have any question, I'll be more than happy to answer those.